Hello, calculus students. Here are your notes for section 7.3, which is finding volume by sweeping cross sections. So the other sections in 7.3 have also been finding volume, but those have been about finding volume by revolving an area around an axis. In this one, we're going to find volume by sweeping cross sections. So just an example of how these two things are different. Let's look in Desmos. So here's an example of revolving the area. In all of these problems, we always have to find the area first, because we're taking the area of a region and then finding the volume from that region. So in this example, here's this area that we found, and we're going to create a volume by revolving it around the x-axis. So that looks like this. Dun, 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 dun. It creates an object like this. And whenever we revolve around, because a revolution is a circular motion, we end up with a volume that we can split up into disks or washers. Okay. So in all those problems, we ended up with cross sections that were disks or washers because we were revolving it. Now, when we're finding volumes by sweeping cross sections, it's going to be a little bit different. Let's wait for this to load. So we're still going to start off by having a base that we use kind of like as an area. Come on, GeoGebra. Okay, so in this example, you can see my base here is the region bounded by this blue graph and by the red graph. It looks like the parabola and a square root function. So our region is the space in between it. And this is kind of like what we're going to use as a base. But instead of taking this region and revolving it, we build the volume on top of it. So we use squares or triangles or circles to make this a three-dimensional shape by using this as the base. So sweeping cross sections means that we just move, let's do a square. We move some shape across it. And that square gets smaller or bigger depending on the width of the cross section. Okay? So if we add more squares and add more and add more, this turns into a solid. This is now a solid object because I've added so many squares. This is three-dimensional. I'm not rotating it around though, so I don't always have circles. The area that we're going to use now is going to depend on whatever shape we use for the cross section. So we can do squares. I could also change this to like semicircles as we saw. So more and more semicircles will create a different shape. So we just use whatever our base is and build upon that base. You can see I'll add triangles, how different the shapes turn out depending on what shape you use. And then squares will be the biggest, like that. Okay. Alright. So back to our notes. Finding volume by sweeping cross sections. I'm just going to write down what our general definitions are going to be. And we're going to have two of them, depending on if we're sweeping perpendicular to the x-axis or perpendicular to the y-axis. So in these cases, as you can see, this purple bar is moving, this bar over here, is moving perpendicular to the x-axis. So the semicircles that I add are being added as changes in x. So this is a dx problem because it's perpendicular to the x-axis. So our two different types of problems will be different depending if we're sweeping perpendicular, this means perpendicular, to x-axis, and this will mean we have a dx problem. Or if we sweep perpendicular to the y-axis, which would be a dy problem. Okay. So the two different volume formulas that we're going to get, the first one, my volume will be the integral from x1 to x2 of whatever the area of my shape is in terms of x dx. So you just need to make sure that whatever this area formula is, it's the area formula for the cross section, meaning the shape, the cross section, in terms of x. Okay. So you can pause the video and try to figure out what the volume will be if we sweep perpendicular to the y-axis. So pause that, try to guess it, and I will write it down now. So it's the integral from y1 to y2, the area in terms of y, dy. So if you need to, you can make a note that this area formula is in terms of y. God, I hope my head wasn't in the way the whole time. Okay, so these are my general formulas that you can always go back to. We're always integrating the area, just as we were with the disc and the washers. It's just those were always circles, and now we're going to have different shapes too. Okay. So let's do an example. So example 1 will be to find the volume of a solid whose base is x squared plus y squared equals 1. So this is my base, or my region, and whose cross sections are squares perpendicular to the x-axis. So you're finding the volume of a solid whose base is x squared plus y squared equals 1 and whose cross sections are squares perpendicular to the x-axis. So we need to do a little bit of careful reading. Of course, we have this as our base. Our cross sections are going to be squares, and they're perpendicular to the x-axis. So when we draw this, we need to be careful. But that's going to be my first step anyway. So in my steps, just so you know, there's going to be 1, 2, 3, 4. But my first step is going to be to sketch the base. I'm going to sketch the base. This one's pretty easy. This equation, x squared plus y squared equals 1, should jump right out at you. This is just a circle. It's the unit circle. Okay, with a radius of 1. If we are sketching this perpendicular to the x-axis, then this is a dx problem. So if I know this, the lights just turned off on me. If I know this, That means that this is a dx problem. So I need to solve for y. Okay. So I can solve for y for this in my head. Basically, I know that x squared plus y squared equals 1 will give me y equals plus or minus the square root of 1 minus x squared. So I have two equations. I have this top one, which is y equals plus square root of 1 minus x squared, and I have the bottom, which is y equals negative square root of 1 minus x squared. Okay. So I've kind of already started step 2, which is to figure out if it's dy or dx. And if it's dy, then basically you solve for x. And if it's dx, you solve for y. And this is the one that we've done. It's a dx problem. And then, find limits of integration. Since it is a dx problem, we're looking for the changes in x. So I'm going from -1 to 1. Okay. So the third step here will be to find a of x. I'm finding a of x in terms of x since it's a dx problem. Okay. So a of x is going to be a square, basically, since it's I'm drawing my cross sections as squares. So if you want, you can sort of imagine it in here. Okay. You would just draw, you don't have to draw this. You can just draw the line if you want, but I kind of outlined what that square will look like. And that's the same square that's over here. Okay. So we need to figure out the area formula for this square. I know that, or we all know that, the area of a square is just the side squared. But we need to figure out how are we going to calculate this side. Because this is calculus, the side length is always changing. Look, if we slid it over, the side length would get bigger and bigger and bigger, and then smaller and smaller and smaller. So these side lengths are always changing. We need to calculate them. So this side, basically, is we can use what we've learned about like finding lengths using calculus. This side is going to be this upper function minus the lower function. So this length is going to be the upper function minus the lower function. It's always changing because the top is changing and the bottom is changing. Okay. So the upper function is positive square root of 1 minus x squared minus the lower function, which is negative 1 minus x squared. So I end up getting 2 square root of 1 minus x squared. This is my side. So if I plug that back into my area equals 2 times the square root of 1 minus x squared squared. Okay. You can simplify this a little bit if you want. The area equals 4 times 1 minus x squared. I'm just going to leave it like that. And you will see why I don't necessarily need to do all the simplification, because at this point, the problem is much easier. My last step is just to find the V total. So I'm just going to find the volume. If you look up above at your notes, you see the equation for the volume, which you should all know is going to be V equals the integral between x1 and x2, which is just -1 to 1 of a of x dx. Now I already figured out what my a is, so I can plug that in. And I get the integral between -1 and 1 of 4 times 1 minus x squared dx. We could all do this by hand, I'm sure. We could do this by hand, or we could just plug it in our calculators. If you want to do that for practice, you can. You should end up getting 16/3 units cubed. Okay. So once you fully just plug in your area formula into the equation, you really can just use your calculator or go back to the old integration techniques that you all are experts on. So the main thing for these types of problems is knowing which way your cross section is going to go and then figuring out what is the area of the cross section. Okay, we're going to do one more, or actually, your next piece of notes, we're just going to talk about common cross sections. In this one we did a square, and as we saw in the GeoGebra tool, there was squares, triangles, and semicircles. But we're just going to figure out what some common ones are. So common cross sections. Are we have circles, circle, semicircle, and a quarter circle. Okay. These areas you should all know pretty quick. The area of a circle equals pi r squared. Semicircle will be pi r squared divided by 2. And a quarter is pi r squared divided by 4. And what these look like, you know a circle, but a semicircle is just a half circle. With these ones, you need to be careful that for the radius, you only use the parts we need. So this is going to be your radius there. It's just half of it. And for a quarter circle, it looks like that. And then you can use the whole bottom, and this corresponds to the radius that you plug in. So you can see circles, semicircles, or quarter circles. As we already saw, there's also a square. For this, the area equals the side squared. And then we have a few different triangles that we can think about. So there's just a regular triangle. There's an isosceles right triangle. And there is the equilateral triangle. obviously for a regular triangle, the area equals base times the height divided by 2. An isosceles right triangle, remember, here's a right triangle. Isosceles just means that you have two equal sides here. So we can basically call these both the base because they're the same thing. And then the area equals the base squared divided by 2. And then an equilateral triangle means 3 equal sides. And the formula for this, I'm not going to prove it. You can do that for fun if you want. The area is the square root of 3 times s squared divided by 4. Okay. So here are common cross sections that you will see and the areas for them. Because in these problems, as I said before, finding the area is the part where you're going to have to think the most. You're going to have to figure that out. Our last problem was a square. This next one will be a little bit more complicated. So we'll go down here to example 2. This one will be to find the volume generated by sweeping semicircles perpendicular to the y-axis. Oops, that says y-axis. Y-axis, my bad. Over the base bounded by the region y equals square root of x plus 2, y equals 0, and x equals 3. There's your problem. Okay, and as usual, my first step will be to sketch and shade. So I need to sketch and shade my region. So first, basically y equals 0 is just my x-axis, like that. And then the line x equals 3, I'll put out here. Here is x equals 3, and y equals 0. And then the graph of square root of x plus 2. So this is my square root function shifted to the left 2. So I know I start here. When x is -1, my function will be 1. When x is 2, then I get the square root of 4, which is 2. And I'm going to end here. When x is 3, my value is just up a little bit between 2 and 3, and this is at square root of 5. Okay. So there's my region. Since I'm doing semicircles perpendicular to the y-axis, this one is actually going to be a problem like this. So this is going to be a dy problem, where my semicircles go up like that. So if we shade it, we should shade it with horizontal lines, kind of like that. And I kind of just left the outline of my little semicircle, my original semicircle. Okay. So as I said before, because this is a dy problem, because it's perpendicular to the y-axis. Then I'm going to solve for y. Okay. So I had y equals square root of x plus 2. Square both sides. I get y squared minus 2 equals x. So when I label that function there, I need to make sure it's x equals y squared minus 2. Oh, maybe someone caught me when I said that. It's not solve for y. Since it's a dy problem, I want to solve for x, as I did. So x equals y squared minus 2. Okay. So I just did step 2. I figured out, is it a dy or dx? And it is a dy. And that also means I need my limits. So, and limits of integration. I'm going to end up integrating between 0, and then remember my top point was this point here at 3 square root of 5. So my highest y value is square root of 5. So kind of just to help me remember when I'm integrating. So when I'm finding my volume, I'm going between 0 and square root of 5 of a in terms of y dy. This is what I need to solve. So my next step, I have my integration. I need to find my area in terms of y. So this is step 3. Find a of y. So in order to do this, again, I'm just going to draw a little cross section over here in orange. Here's my orange semicircle. These semicircles are changing throughout. They'd be really, really small here, be a little semicircle, and a bigger semicircle down here. So I need to figure out what is this radius. What is this area, first of all? So the area is going to be pi r squared divided by 2. And in my formula, I need to figure out what's the radius. Okay, so what is the radius? The radius here is this distance from my function, so from y squared minus 2 to 3. So to calculate this radius, just as we could find like the area of this region, I can do that radius is the right function minus the left function, but divided by 2, since it's only half of it. I want half. So it's like my right minus my left. Just like in the other problem, I did upper minus lower. This is right minus left. So this right function is x equals 3. The left function over here is y squared minus 2. And this is all divided by 2. So to simplify just a little bit more, we have 5 minus y squared divided by 2 is my radius. Okay, now I plug this back into my area. So I'm going to plug my radius into my area function. So my area equals pi times 5 minus y squared divided by 2 squared divided by 2. Don't be overwhelmed. This is just algebra. It's okay. So if I simplify this, the area equals pi over 2 times, I'm going to split this up, 5 minus y squared over 4. So basically I just distributed the square to that and got 4. And I'm just going to leave this as pi over 8 times 5 minus y squared. You can go back and check my work if you need to. So here's my area. I accomplished that, the hardest part. Now my next step is just to find the volume. So find V total. And I do that by plugging it back in here. My volume is my integral between 0 and square root of 5 of pi over 8, 5 minus y squared dy. And if I have my calculator, I'm all good. Just put this in your calculator. You get 11.708 units cubed. So just as in the other problem, the most thinking comes in this part here where you have to figure out what is the area of the cross-section, because the area is always changing. You should never get just a normal number for the area, because then this is no longer a calculus problem. That could be a problem you did in algebra. I guess if you do, then it's an easy problem. You just have a normal shape. But because this is calculus and the areas are always changing, you should come out with some sort of formula for that. Okay, so that's it pretty much for your notes. I'm just going to leave you with one more problem that I'm going to let you try. So this one you're going to try on your own. It's find the volume of the solid formed by sweeping squares perpendicular to the x-axis over the region bounded by y equals x squared and y equals 9. So you should follow the steps. And in the end, so you can check yourself, the answer is going to be 259.2 units squared. I want you all to try this, and we will go over it in class tomorrow. All right. Good luck, calculus students, and see you tomorrow.